Hey, and we're recording. Sorry, we missed the first couple of problems. Thank you very much to Paul and to Austin for pointing out my faults as a teacher. I'm such a terrible teacher. It's okay, I'll get over it. Okay, so we just got done taking a look at classwork problems 2 and 3, and for more detail, I will suggest that you confer with teams Doc and Paul, respectively, because they have it all figured out. And that brings us to questions 4 and 5. And Team May you go ahead and start explaining your solutions for those?
All right, who wants to explain number 4? Okay, I'll explain number 4.
He says as if he doesn't know the answer to the question. Yeah.
So we had a mass. We had a mass that weighs 12 pounds that stretches a string 3 inches. So we just looked at the equation force equals negative k times y, and we just substituted in for 12 for the force and 3 for the y, and we got a k value of 4.
What are the units?
4 pounds per inch.
Of course, none of these parameters mean anything unless we know what their units are. So if I asked you, hey, what's the m value for this equation? And you said, oh, it's 3. Then I would have to ask 3 what? Because if it's not in the same units that I'm using with the equation, then it's gobbledygook, right? You guys, have you heard the story about what happened to one of the Mars landers back in the late 90s? Did you hear about this?
I think I know.
Anybody who wants to be an engineer. Yeah, anybody who wants to be an engineer really needs to be familiar with this story. The engineers who had designed the craft as it was going to come in and just before it enters orbit. So everything up to orbit, there's one set of engineers, and then there was another set of engineers who said, once it gets into orbit, we're designing how does it land and and all this stuff. And they did their work, and then they communicated with each other, and then they sent all the stuff to NASA headquarters, and they were getting ready to bring this thing in for a landing, and it was coming in, and then all of a sudden they lost communication. They're like, what happened? And it turns out this set of engineers and this set of engineers were using different units. These guys were using the SI system, these guys were using the imperial system, and they done screwed up because they didn't actually use the same units. And so as the craft was coming in, these guys were like, okay, so you tell us how fast it's coming in. And they gave them a number, but they didn't give them the units. And they gave them a number, and they're like, oh, that many miles per hour. Okay. And then they did the calculation, but they totally calculated it wrong. And yeah, they lost about $1.5 billion and about 15 years worth of work for a whole bunch of very angry systems engineers and astronomers and astrobiologists. And you have not seen angry until you've seen an astrobiologist get angry. That's scary stuff. I mean, it's literally out of this world. Anyways, okay, sorry, that was a big buildup just for that one joke. Okay, so we figured out how to solve for K, and it's worth noting this is going to become kind of a fixture in our work. We're going to be looking at harmonic motion and harmonic oscillators, and that means understanding a little bit about springs. And so a spring constant is one of those concepts. It's a physics concept, but we're going to use it, and so you need to be familiar with it. So you guys also had number 5. So would someone else like to explain number 5? Because Chris did such a terrible job with number 4. No, you did great, Chris. I'm just kidding. Hold on. Let me gather that shade back. Okay. Anybody else? What's that, Quentin? You really want to? Okay, go ahead, Quentin. You can explain number 5. You owe me, pal. Go ahead.
Okay, so number 5. Do the springs in an extra firm mattress have a large spring constant or a small spring constant? We were saying large because then it wouldn't the spring wouldn't stretch and compress as much, they wouldn't be all bouncy and stuff, I guess. And for the extra firm with the large spring constant, it would just be a very small amount of distance moved.
So a way of thinking about it would be, you can think of the spring constant as the stiffness constant of a spring. So if it's really, really high, that means your spring is very, very stiff, very hard to compress, but also very hard to stretch as well. So those of you who drive what's called an automobile may be familiar with the concept of shock absorbers, which are primarily built around springs and springs that have some damping going on. But the springs themselves are incredibly large in terms of their spring constants. They have ridiculously large spring constants. Have you guys ever, has anybody ever seen the spring from inside a shock absorber? Played around with it? I mean, have you tried to compress it or stretch the spring that's in a shock absorber?
No, I mean, I tried and stuff, but you can't even move them. They're ridiculous. They're probably the ones I got on my car about half an inch around in diameter just for the coils and stuff. And there's no way anybody in their right mind could easily move one of those.
Now, with your bare hands, there's no way you could create enough force to compress them, right? Because they have like a force rating of something like thousands of pounds per inch. So you would have to generate literally thousands of pounds of force to compress that spring 1 inch. And so as a matter of fact, if you look at a shock absorber, one of the things, a tiny little writing on the shock absorber will be a K value. It'll actually tell you what the spring constant is for those springs. And if you go into, it used to be this way in hardware stores, but I don't know, I haven't been in to like a Home Depot or anything like that recently. But in the old days when it was like Kessler's Hardware downtown Jackson, and you'd go in and be like, I need to buy a spring for, you know, something that I'm doing, they wouldn't ask. They'd just say, okay, right over there. And you could actually buy the springs based on the spring constant, and they would have fixed, units. So usually pounds per inch. Or something like that. And so, you know, you could buy a spring constant that was really, really high. The bigger the spring constant, the stiffer the spring will be. And sometimes a really stiff spring is important, and sometimes it's not. Sometimes we want to have springs that are much easier to compress. Like, I don't think I have an actual ballpoint pen where you kind of click on it. Those springs are incredibly weak, right? They take like almost no force at all to compress quite a bit. So those have a tiny little spring constant, but you wouldn't want it to be too big in that context. So, what's that? Slinkies. Sorry, the peanut gallery over here is saying slinkies. Like, you even know what a slinky is. Do you even know what a slinky is? Do you?
Yeah.
Of course they know. Everybody knows. Everybody wants a slinky.
Absolutely.
Absolutely. Oh, they're saying it again. Why can't you be our teacher? God, you're so mean,
actually
guys.
They were actually the byproduct of an anti-aircraft recoil system during World War II, and the guy brought it home and his kids started playing with them, and they realized it'd be a good toy.
Yep. It's a tremendous story. Between that and the story behind Silly Putty, where Silly Putty comes from, those two are like my childhood. You know, that's everything. Because, you know, after the Great War, you know, we didn't have much in the way of toys. It was just you know, newspaper that we had to make into like figures and old anti-aircraft springs that we. No. Okay. Anyways, so that gets us through number 5, and each of the groups I asked to take a look at number 6, because number 6 is kind of, for chapter 2, it's one of the main types of problems that we're going to be dealing with, which is, if I give you a context, can you model it with a second order differential equation? And so in number 6, it says we've got a mass that weighs 4 pounds and it stretches a spring 4 inches, which means we could calculate its K, its spring constant. The mass is extended 1 foot from its rest position and released with no initial velocity. And then it says for part A, formulate an initial value problem consisting of a second order differential equation and 2 initial conditions that correspond to the motion of this undamped mass spring system. So my question to you is, where in all that text did I say anything about initial conditions? And how is it, there's 2 of them in there. Did you spot it?
The 4 pounds and 4 inches.
The 4 pounds and 4 inches, that actually not initial condition, but it's one of them is a force and one of them is a distance. So that first sentence is not about the initial condition. That's about being able to calculate the K value, the spring constant.
Oh, it's the 1 foot, and
Yeah.
wouldn't the 4 pounds go into the force side of the equation? You don't need the 4
no
pounds at
initial
all.
velocity.
Yeah, no, the only reason that we would use a measurement of force would be to calculate a spring constant. Because the equation that we're going to be doing, that we're going to be setting up for this, and it's okay, I'm going to switch over to my document camera here. So hold on, hold that thought. The equation that we're going to be looking at in 2.1 and a little bit in 2.2, and this is our second order simple harmonic oscillator. So we're doing this for show. That was bad. Okay, anyways, the simple harmonic oscillator equation says that if you have your mass times the second derivative of position with respect to time, plus your spring constant times your position, that's going to equal 0. And this, by the way, comes from, and it's that second part video for section 2.1. That was me building this equation. And I built it based on Newton's second law. I'll just say this comes from F equals ma. That's Newton's. The net force on an object is equal to its mass times its acceleration. And the other equation is the restorative force is equal to negative k times y, right? And so this is the F equals ma part. This is the k times y part. It was on the other side. We moved it over here and made it positive. So this is our second order differential equation. All I need are these two values right there to be able to do stuff with it, to be able to solve it. So if we start with knowing in this case that our mass is equal to, what was it, 4 pounds? And our K value, if we know what the K value is, we can plow ahead. So K, thanks to Team May, I think it was Team May, yeah, Team May, they taught us that if you take your force divided by your mass, you can actually calculate your spring constant. Now you'll notice this is the absolute value of that, because the spring constant is always a positive value, right? And so for us, that first sentence says a mass weighs 4 pounds and it stretches the spring 4 inches. And so the K value that we're working with is 4 over 4 is just 1, and it's 1 pound per inch. So notice we're using pounds for mass, pounds per inch for K. What does that mean the units of Y must be in?
Would it be per inch?
Well, it's the per inch is attached to the K value. K is pounds over inches.
Pounds.
So if this is in pounds per inch, the units for Y has to be in inches in order for this whole term to be a force term. Pounds.
Oh, okay.
Does that make sense? So we know from this right here that we're going to have to be talking about inches. So this piece of information tells us that Y of t is in inches, right? Has to be. Anybody see a problem? There's one small problem with this. It's actually a big problem. It's the engineers at NASA problem, but not quite.
Did we kind of used 4 pounds as a force and a mass?
Thank you. You spotted it. I used it over here. 4 pounds is a force because pounds measures weight, which is a force. We are so used to, in this country, thinking about pounds being interchangeable with mass, but it's not. The mass is not 4 pounds. The mass is some other crazy unit, but it's not pounds. Pounds is force. So this cannot be the mass. This is actually the weight. So how do I get from weight to mass? What's the relationship between weight and mass?
Wouldn't mass be in slugs?
It's going to be, yeah. So what's the equation? What's the relationship between weight and mass? Weight equals
Mass times acceleration.
mass times, specifically, gravitational acceleration, right? So you've probably seen F equals mg or W equals mg, mass times gravity. The mass is what we're after, but we don't have the mass, we have the weight. So what I need to figure out is, how do I manipulate this so that we're talking about weight instead, or excuse me, mass instead. And so the equation manipulated would be mass is what we get when we take weight and we divide it by gravity. But the units have to make sense. They have to play nice with each other. So the weight is going to be in pounds. So this would be 4 pounds. And the gravity, I can't use meters per second squared. It's going to have to be in imperial units. So distance per time squared. And I think you'll see on that particular problem, I say the acceleration due to gravity on Earth is approximately 9.8 meters per second squared, or 32 feet per second squared. Now, you might not recognize what pounds over feet per second squared is as a unit, but this actually has a name. This is 4 over 32 is 1/8, and this is 1/8 of a slug. This is why we don't use the imperial units, because it's ridiculous. Who talks about slugs? Unless you're talking about weapons, or you're doing, I don't know, Iron Age blacksmithing or something like that. I don't know. Nobody talks about that. But turns out that this unit is commensurate with pounds and inches and all that other stuff. Right? So if we take our units and plug this thing in and say, now our equation can be written as 1/8 y double prime plus k, which we said was 1, times y equals 0. This is the differential equation for our initial condition. But we also need initial conditions for our IVP. So where are we going to get the initial conditions from? And you guys have been quiet for too long, so I'm going to shut up and let you talk.
Wasn't it still going to be off since we used inches for K and feet for the
You are
math?
so right. You are so right. Sorry, I forgot about that. Yeah, sorry. I'm getting ahead of myself. This is not going to be 4 inches. We're going to convert that. It would be 1/3 of a foot there. And so this would be 3 pounds per foot. Sorry about that. Good call on that. Oh no, it would be 12 pounds per foot. 4 divided by 1/3 would be, yeah, 12. Duh. Sorry. Good catch. Yeah, I was running ahead of myself. I knew it was going to be slugs, but I forgot about that. So 12 pounds per foot. And so this is 1/8, and this would be 12 right there. Boop. Whew. Save. So what are our initial conditions? And where do we see that in the text? Again, this is the part that Maple doesn't do. So you could type the equation into Maple, it knows what to do, but you can't type the text of the problem into Maple. So where's our initial conditions in that?
Initial conditions are the when it's extended 1 foot from its rest position and
1
released.
foot from, and extended means positive or negative y value.
Positive.
Yeah, extension means we're stretching the spring, which is always, the default for us is that's in the positive direction. So we've got some initial conditions to consider. One of them is it's going to be t and a y value. And so this is at 0 time, this thing is stretched 1 foot? So it says, yeah, 1 foot. So at 0 seconds, it's 1 foot. And then the other initial condition, it's pretty subtle, but it's there.
It's released with 0 velocity.
And it's released at t equals 0 with a velocity of 0. So at 0 seconds, it has 0 feet per second. So we actually have some initial conditions, 2 of them. Why do we need 2 initial conditions?
Because we're going to have 2 constants, right?
Yeah, because it's a second degree differential equation. A second degree differential equation requires 2 initial conditions. A first degree differential equation requires 1. Hey, guess how many initial conditions you'd have to have for a 4th order differential equation?
4.
4, because you'd have to integrate it 4 times to get to your solution curve, right? And so you'd pick up 4 integration constants along the way. It's just the nature of the beast. So now we can hop over to Maple and see what this is going to give us. So I'm going to share my Maple screen and cross my fingers and hope that it works. Maple's been giving me trouble lately on this computer, but here we are in Maple, and notice I start off the document from here on out always with DE tools. That allows me to do DE plot and all the other stuff, but also with plots, because plots is what allows me to do the stuff in 2.2, like field plots and vector stuff. So the fancier plots I can do with that. So I've got my differential equation, so I'm going to just call it DE, and I'm going to name it DE. Will be 1/8. I'll call this times the second derivative of y. So I'm going to be cheeky and use this second derivative of y with respect to t plus 12 times y of t equals 0. See, this is, yeah, it's being really weird. It's taking its time every time I hit enter. So I've named my equation. So I can, if I wanted to, I can say dsolve, and I'm going to set this up with brackets in here because I'm going to use not only my differential equation, but I'm also going to type in my initial conditions. And my initial conditions are, see, y of 0 equals, was it 1? And the other one was y prime of 0 equals 0. So I'm saying, hey, Maple, I've got this second order differential equation. I've got these 2 initial conditions. Can you tell me what the particular solution is? And Maple says, yeah, sure, here it is.
I have a quick question.
Yeah, sure.
How did you get the prime symbol?
Oh, it's just literally the single quote. So right next to your enter key or your return key, it's right next to that, just single quote. And so notice, because I've defined what it's taking the derivative with respect to there, when I say prime, Maple goes, oh, okay, you mean the first derivative with respect to the same variable. So it doesn't give me a hard time. So what do you notice about the particular solution? What is it predicting my mass on a spring is going to behave like?
A wave. Okay.
Is my mass on a spring going to go like this?
No, but like through time.
Yeah, and so that's the key. This equation does not actually show me the motion of the mass. It shows me the motion of the mass as a function of time. So when I plot this thing, and oops, come on, Maple. There we go. If I say plot the right-hand side of number two, boop, and we'll say t goes from 0 to, I don't know, 5. We don't have to go that far out. We get a curve that it's the cosine function, right? With a particularly adjusted period. But you can see you've got this cosine curve, and it just kind of wobbles back and forth. But what we're seeing on this graph is not what the mass would look like. If you want to see what the mass would look like, imagine taking this graph and rotating it so that you're looking straight down the time axis. And that's what you would see. You'd see the mass start up here and go, woo, 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 it would just go back and forth this way. You don't see the time dimension because that's moving away from you, right? So this graph is not the picture of reality, but it's showing us what to expect over time. Now, part B says, using Maple, find the equation of the solution and then predict its location 1.3 seconds after release. So how do I do that in Maple?
Just write y of 1.3.
Yeah, I can just say, hey, I know how to input this. I would, just because I'd like to refer back to it, I would say, hey, Maple knows this equation as number 2. And so I would just say, evaluate the right-hand side of 2 when t equals, is it 1.3? 1.3 seconds. And of course, it's 1.3 seconds, not minutes, not hours. So that should work. And Maple gives me, because it's very obliging, it gives me the exact answer, cosine of 5.2 times the square root of 6, right? But I want to know what that is out to a certain number of decimal places, and so I can just say, convert this output, or what's the fancy way of doing this, off to the side here on the context panel. You can say, hey, Maple, how come I'm not getting my, there it is, approximate out to like 5 decimal places. And so Maple says, oh, okay, 0.98542. Now, how do I interpret that? What is that number? First of all, what units does that have? Second of all, what does that mean?
It's in feet, right?
Okay, so 0.98542 feet, where would that be?
It'll be down, like from or below the resting position of the spring because it's positive. So that means the spring is stretched.
So the string is, so this is 0.98542 feet stretched away from the rest position. And it's positive, so we know that it's when the spring is stretched. And that's different than if I were to look at a different time, if I were to look at like, I don't know, 1.5 seconds or something like that. 1.5, I get an answer that looks like this. And then if I do approximate 5 decimal places, I get a negative answer. And again, negative doesn't mean bad, it just means it's compressing the spring. So at 1.5 seconds, it's compressing the spring. At 1.3 seconds, it's stretching the spring. And again, we have to be smart enough to be able to interpret the output of what Maple says and keep track of the units and be able to make sense of this in terms of the units. So.
Can I ask a quick question?
Sure, yeah, definitely.
I forgot. How do you get that? You do the right-hand side RHS. How do you get that special 2 to know?
Yeah. So if I wanted to refer to, if I wanted to evaluate the right-hand side of number 2, I do, for me, I'm on a Mac, I do Command L. If you're on a PC, it'd be Control L. And so Control L is basically label. I like to think of it as line because of the line numbers. And so I'm referring back to a certain line. And so I would say line number 2, and then evaluate that when t equals, 16 or something. And Maple says, no problem, I can do that.
All right, cool. I just forgot how to do it and couldn't remember.
Yeah. No, it's okay. It's one of those things where the more you use it, the more you remember it, right? It's, if you see somebody do it and you go, oh, that's cool, I should remember to do that. You really just have to start doing it. And once you do a couple times, you'll remember.
How would you find this graphically?
How did I find it graphically?
Yeah,
I found it to be pretty nice. I'm not gonna lie. I found it quite nice.
Mm-hmm. Like, how would you tell Maple, hey, I want to see what the value is? Because like one of our first assignments, you asked us to do something just using graphical techniques.
Yep.
And I couldn't. I used like a little pointer thing, and apparently it wasn't. You marked me down.
No. I think I probably marked you down because, so for example, if I look at this graph, and this is actually a really good segue. If I look at this graph and I asked you to predict a particular output value for an input value, and I said at t equals 2, and you'd be like, okay, t equals 2, I can kind of go up here and go, I think it's about right there. Now look at the scale on the vertical axis. Can you guys see it okay? Is it big enough for you to be able to see? Let me see if I can bump up the size here. Maybe I can do that. I don't know. But when t equals 2, it looks like it's right about here. So I would call that 0.7. But notice the scale. The best I could do would be 1 decimal place beyond that. The best I could do would be like 0.71 in terms of precision. If you're thinking about like reading scientific equipment, the best precision that I could come up with for that prediction would be like 0.71. That'd be my guess. Some of you were giving me precision out to like 4 decimal places. Like you'd be like, oh, that's definitely 0.7162. I'm like, how the hell did you get that from the graph? There's no way you'd be able to go out 4 decimal places. And I think it's because, this is my hunch, it's because you were using some kind of a pointer system, or you had actually calculated it and came up with the solution some other way. But just based on the graph, estimating from the graph, you have to use the precision of the graph, whatever that happens to be. So one way that I would do it is I would say, look, I'm really interested in a t-value. Oh, whoops. I'm really interested in a t-value right around 1.3. So if I said 1.25 to 1.35, I make my scale go that tiny little distance. Watch what happens to my graph. And take a look at what happened to my scale as well. My ability to be precise has gone up.
I used a little, like Maple has a little pointer tool.
Sure,
thing.
yeah. If you click on the graph up here, there's
Yeah.
some other options up here. And so I think one of them, it stays tracked on the graph. So for example, doing it this way, those numbers are probably too small for you to see, but yeah, you could totally do that.
But
And
is
so
there a way to say, hey, Maple, I want you to like mark a little mark on the graph and tell me where that is?
that is an excellent question. The answer to which is, I don't know.
Oh, fair enough.
Probably, but I've never found it. I've never come across it. Nobody's ever shown it to me. And
I remember that question. We were looking for like when 2 graphs intersect.
yeah,
and
yeah.
I was trying to find out if there's a way to have Maple find intersections like you can on a calculator.
Oh yeah, absolutely you can do it. But the reason that I chose that particular problem was that it wasn't solvable analytically. Maple would freak out and you wouldn't actually see all the solutions. That's purposely why I chose that, because I wanted to force you to do a graphical estimation. And if you go back and take a look at it, it says estimate it graphically. I'm not looking for the right answer. I'm looking for best guess. And so for right now, I would say I'm at 1.29989 for the t-value. That's a pretty close estimate for 1.3. So I'd be pretty confident in that answer. But if you wanted to, you could even go further and say, I'm going to go from 1.29 to 1.31, and then take a look at what happened to the precision on that axis now. So every time you kind of zoom in, you're getting more precise. You're getting closer to the right answer. But graphs are inherently approximate, right? Anytime you use a graph, you're always approximating, no matter what. And if I wanted to, I could go, okay, 1.295 to 1.305. And we get even closer. And you can keep doing this to your heart's content. And eventually you'd feel comfortable enough with your estimate and say, okay, I think that's pretty much dead on right there. That's good enough. But you'd recognize that you're limited. It's an estimation. Sorry, I wish I had the answer for, damn it, Maple, just tell me what it is right there. And the short answer is, with this plot, I don't know what you call it, the reticle that kind of follows the graph. That's the closest thing that I've found to it. So. Any other tech questions or questions about that? Well, I've got one. We have our differential equation up here, right? What happens if I ask Maple to say, give me a DE plot of that differential equation? And I know my dependent variable is y of t. And we could go from t equals, I don't know, 0 to 5 or something like that. And we could have y go from, I don't know, -2 to +2. If that's all I did, I just want to make a DE plot. And I hit enter right now. What do you think Maple's going to say?
No.
Maple almost never says no, but it will say error. Notice the error though. Cannot produce plot. Non-autonomous DEs require initial conditions. You're like, non-autonomous DEs? Our differential equation, that's autonomous. Everything is in terms of the y variable. But remember, Maple's thinking you're going to try to plot a single differential equation that's first order, because it sees y of t is your dependent variable, but your differential equation contains not just y of t, but the second derivative of y of t. So Maple doesn't know what to do with this. But watch, if I include initial conditions, specifically the two that I know, so if I say, for this one, if I do y of 0 equals 1, and then the other one is y prime of 0 equals 0. If I include those initial conditions, let me make sure everything's delimiters are correct. And of course, I have to tell Maple I don't want that pukey color. I want the line color to be blue. It says, oh, too few initial conditions, y of 0 equals 1. It does, oh, I think it's because I need to have them together. That's what it is. Sorry, apologies. They have to be together because they're technically one set of initial conditions. Look at what Maple gives me. Does that look familiar? Look at the axes. You guys are quiet. You're stunned.
Are we supposed to say anything?
I'm really curious. It should look really familiar. It should look like what we saw when we did this graph. We plotted the solution curve from 0 to 5. That curve and that curve should look like the same thing. The only difference is the vertical axis up here is from 1 to -1 to 1, and I can change that, make it look exactly the same.
It's like the dollar store version of our first.
It's the dollar store version of the first curve. They are literally the same thing. So I could use DE plot to do everything all in one fell swoop. The problem is it's kind of herky-jerky. How can I make that herky-jerkiness go away? What could I do? What extra code could I add in here to make that herky-jerky go away?
Is
Didn't
that
you add
none
more
point?
points or something, if I remember right?
Say it again.
You add like more points, like it takes into more points when it creates a line.
Yep. And if you remember back to our Euler's method days, we had num steps was one, and then the other one was step size. And the step size is the one for this one. So if I make the step size smaller, I don't know, so I'll just try 0.1. Let's see what we got for that. Well, that's not that great. Let's try 0.01. Better. Suddenly that curve and that curve are looking pretty much the same. All right, I can shrink it down vertically a little bit to give it a little bit of zazz. Look at that. Now, what did I accomplish by doing this in a DE plot? I accomplished the fact that I didn't have to solve the differential equation and then plot it. I told Maple, I want you to make me a plot of the solution curve for this differential equation with these initial conditions. So I can do that in Maple to get a plot of a solution, but For a second order differential equation, the only way that I'm going to see a DE plot is to see an actual solution plot of the curve. I can't get a picture of what the phase plane looks like, or if you want to think of it as the slope field. There's no slope field for this because it's a second order differential equation. The best I could hope for would be to turn it into a system of first order differential equations, which I can totally do, and that's what we're about to do in a second. So if we have our second order differential equation, we have stuff that we can do in Maple. We can solve it. We can plot the solution. We can make predictions about the solution. All that stuff is available. But we can't see a vector field for this. It's not there. So let me drop the Maple screen for a second, go back to our doc screen, because I want to talk about this, because if this is my second order differential equation, what is the equivalent system of first order DEs? And that, my friends, is your next task that I would like you to figure out. If that right there, and you might want to write it down if you haven't already, if that right there is our second order differential equation, I want you to turn that into a system of first order differential equations. And if you've watched the videos, you've already done this. Now I'm asking you to do it with a slightly different differential equation. Okay, so I'm going to put you into breakout rooms here. So let me stop the share. And I'm going to open up the rooms, and I want you guys to, I'm only going to give you a couple minutes with your team, come up with a system of differential equations, first order differential equations, and then I want you to make me a DE plot for that system. Go to it. And I'm going to hit pause on the recording because you don't need to watch me sit here and drink my soda. So we're going to resume recording by taking a look at how to turn that second order differential equation into a system of first order. We got the system, and so now we're going to make a DE plot. And the first equation is our derivative of y with respect to t. That's just equal to v of t. And again, we have to treat these like they're functions. So it's got to be v of t, not v, not just v. And then the other equation, that's the derivative, of v of t with respect to t. And we said that that was equal to negative 96 times y of t. Okay. So notice inside that first set of brackets, that is my system of differential equations. The second thing that I have to type into my DE plot is my dependent variables. And the order does matter. I'm going to put the order in the way I think about horizontal first and then vertical. And so I want y of t and then v of t. Right. And by the way, that's the same order that I listed their differential equations. So if you put them out of order, you're going to get really weird results. So if you remember, we've done DE plots before. The differential equation was first, then the dependent variable, and then the independent variable scale. And the independent variable for this is t. And so let's go, I don't know, t is 0 to 5. I'm just making stuff up. Because remember, on the phase plane, we don't actually see time. The only way we would see time is if we had a curve that we were drawing. But we're not going to include initial conditions, at least not on this first graph. So I have my t value. Next is the dependent variable window scales. So my y will make it go from, I don't know, negative 5 to 5. And the v is the other direction, the vertical direction. And we'll make that go from negative 5 to 5. And if I stop right here, I now have a DE plot, which is going to be for this, the direction field. It's going to be the vector field, but without the lengths of the arrows changing. And so if we take a look at this, we see something that looks like this. It's not all that exciting. And it's the reason it's not exciting is because that's a really big number right there. And so you'll notice we have all these arrows on this side are downward pointing, all the arrows on this side are upward pointing, and right near the V axis, that's where they kind of change direction. And so if we did an initial condition, we would see kind of a really weird looking oval shape on this graph. So we can add an initial condition that goes right in here, right nestled right after the independent variable. And so I think for our initial condition, it was 0, 1, 0. If I remember correctly, does that make sense? So 0 for time, 1 for position, and 0 for velocity. I think that was our initial condition. This is the audience participation portion of tonight's program.
Yes.
Thank
It
you,
was.
Chris. You don't even have the super fancy microphone like some people, but thank you. Okay, so let's see what we get. Oh, before I hit enter, line color, anything other than that pukey, yellowy stuff. We get a curve that looks like this, and our scale is such that it doesn't even go down far enough. So I'd have to change my vertical scale in order to be able to see it. So I'm going to make it go from, I don't know, -20 to +20. Maybe that'll be enough. Let's see. Hey, look at that. We didn't have to go that far. 10 would have been enough. Okay, so we'll make it go from 10 to 10. Now, what the hell's going on? Why are all these like, why is it all fuzzy? Why is it jumping all over the place? What's going on? Remember, what we see on this graph isn't reality. It's the phase plane, which is position this way and velocity this way. So why is our curve all jumbly and jumping all over the place?
We're taking too big of steps.
We are going, there's two ways to think of it. We're taking too big of steps, but that's because our time increment is quite big. What we're going to find out is if I go from 0 to 1, it's still going around the cycle. And just at 1 unit of time is more than enough to get through one cycle. Just to refresh your memory, if I scroll up, 1 unit of time is from here to here. Notice it goes from here down, back up and down. So it's actually completed 1.5 cycles in 1 unit of time, 1 second technically. So I didn't have to have the t value go from 0 to 5. The other way to solve that problem, as Stephen was suggesting, was, hey, you're taking too big of steps, so decrease the step size. So I could force the step size to be smaller, like 0.01, and still go from 0 to 5. And I have a decent enough curve, right? So there were two ways to fix that problem. One was, whoa, you don't have to go so many cycles to be able to see what the curve looks like. The other solution was, you can go that many cycles, just take small steps, and Mabel can hang with you on that. So this graph right here, again, not a picture of reality, but it allows us to say things like, oh, so if you have a positive y and a positive v for your starting initial condition, you know exactly what's going to happen over time. Over time, this curve moves in a clockwise fashion, so your curve is always going to move like this. And I can also ask the question, based on this phase plane, is there any reason to believe that our mass will come to rest?
No.
Because come to rest would correspond with what location on the phase plane?
Going to 0 on the y-axis.
0 on the y, and rest, meaning not moving. So
The 0 on the v-axis.
yeah, so the origin, right? The origin, we would expect no motion, no velocity, and no positional change. So this is at an equilibrium point, but this curve never approaches equilibrium. That's because there's no friction involved. That's what we invent in section 2.3. We invent friction in our system, and that changes things. You can modify this just slightly, by adding a friction term. And by the way, the friction term goes in the velocity equation. And all you'd have to do is add something in like minus 2 times v of t. And watch what happens to my curve now. Again, this isn't reality. What you're seeing is not the motion of the object, but what you're seeing is the phase plane that allows you to make predictions. At an initial condition of one foot positive position, but 0 velocity, this thing starts moving, and it kind of goes around like this, and the cycling in towards the center corresponds to it's headed towards equilibrium. Over time, this thing will head towards equilibrium. And by the way, if I were to change this from 0 to 1 second, we wouldn't see all of that motion. We would only see about 1.5 rotations, right? So we can control how much of the curve we see on the phase plane by altering the independent variable, the time, right? We can change the herky-jerkiness of the curve by changing the step size. So if I make this thing go from 0 to 2, we'll see a little bit more of the curve. If I make it go from 0 to 3, we'll see a little bit more of the curve. And it's clearly headed towards the equilibrium point at the origin. And so you might say, you know, after 3 seconds, this thing is going to be straight down to basically not moving at all. You wouldn't be able to detect movement. So the DE plot produces the phase plane. Now, what if I wanted to see the vector field? In other words, I don't want just the directions, but I want the magnitude of the arrows as well. How do I produce that? What's the command for that? It's not DE plot. I can't get vector field from DE plot. Somebody who's watched the 2.2 videos probably knows this.
Is it the field plot thing or?
Field plot thing, the field plot thing. As a matter of fact, as long as you have, up at the beginning, as long as you have with plots, then you can make a special kind of plot called a field plot. And the field plot is really just the vector field. And those of you, I think most of you have had Calc 3. I think most of you have had it. And if you've had Calc 3, then you learned about vector fields in a different context. We're going to use them for something different, right? Now what we want to see is not just what direction do the solution curves move, but what's the magnitude of the arrow on that field. In other words, how fast are they moving, the solution curves moving, when they're at that particular location. So field plot, again, I'm going to type in my equations, but for a field plot, I don't have to type in the full equation. I just have to type in the right-hand side of the equation, and they don't even have to be functions. So my first equation, remember, was dy dt equals v, that's the right-hand side, comma, the right-hand side for the other equation was negative 96y. That's it. Those are the right-hand side for my field plot. Then after this, I need to let it know what my scale is for my graph. I have to tell it, okay, so for the y values, the y-axis is going to go from, I don't know, -2 to 2, and the v-axis is going to go from, I don't know, what, -10 to 10. And that's the bare minimum for a field plot. That's all you need. You need to give it what's the vector field that you want to graph, and what window settings do you want to have for it. And so if I hit enter for this, it draws me a vector field. Now, this graph, what we have here, is essentially, if I change the settings, hold on, let me change the settings on this. Get rid of my second term on this one, boop, and then change this from -5 to 2, and that would be -2 to +2. Then it will be the exact same. So notice that graph right here, we can see the direction for the solution curve at any location on the plane. But down here, we can see the direction, but the length of the arrow tells me how fast is the solution curve moving at that point. So pretty clearly, you can see if you're way out here, you are moving really fast compared to being really close to the origin. You're not moving very much at all near the origin. So the further you are out from the origin, the faster the solution curve moves on the phase plane. So this, go ahead, sorry.
The length of the arrow is conveyed by by V.
The length of the arrow is the magnitude of the two derivative values at that point. Remember, this is plotting for us at any given point on the phase plane. You've got a dy dt value. That's the horizontal part of the velocity, or the horizontal part of the slope. And then you've got the dv dt, which is the vertical part of the slope. Put those two together, and you get the direction on the direction field. And the length of that arrow is determined by the size of the dy dt and the dv dt at that particular location. Did that make sense?
Yeah, that makes sense.
Okay. So again, we know that our dy dt is equal to v. So whatever your v coordinate is, that's the dy dt part. So if you're out here at 1, 0, that means your y coordinate is 1, your v coordinate is 0. So this is saying your horizontal part of your motion is nothing at that location, because dy dt is equal to just v, and your v coordinate right there is 0. But your y coordinate is +1, and so that means your vertical, your dv dt, is -96. So this thing is like, it's a really long arrow by comparison. But if you're way out here at 2, then it's twice as long. So they basically have normalized the arrow lengths to kind of show you the longest arrow out here. Those are really big. That's a really big vector, right? But these tiny little arrows in the middle are telling you that by comparison, when you're close to the origin, there's very little motion for the solution curve. So you've got two graphical representations. This one right here is what we get and what we would call the phase plane. Or if there are many solution curves on it, the phase portrait. There we go. So these are the two terms that we use a lot in this. The phase plane is defined as just the direction field for your two dependent variables, right? And the phase portrait is the phase plane, but if you have a whole bunch of initial conditions, a whole bunch of separate curves. And the purpose of a portrait is to kind of show what solutions do on the curve or on the plane, right? This one down here gets referred to as the vector field, or the direction field. And I don't actually use the term direction field, because direction field literally just means what direction are the arrows pointing. So I try to avoid using that phrase. I refer to this as the vector field, and that is showing me not just the direction that the arrows point, but the magnitude as well. And by the way, you can create a DE plot. I think I showed you this on the last time or on the video. You can make, it's on the video, you can make a DE plot, phase plane with a field plot just by saying field strength equals fixed, I think. And so notice, that's the exact same plot as this one with a whole lot less code. So if you ever needed to make a phase plane, you could just use field plot to do it if you wanted to. You don't have to, but you could. So on the, let me stop the share here. On the notes for, or not on the notes, the classwork for section 2.2, there's practice making vector fields, making phase planes, and making phase portraits with sets of a system of first order differential equations, but also I do that with a second order differential equation that you can turn into a system. And then there's some interpretations where you can go backwards. I show you a solution curve on the phase plane and I say, what do we know about the equations? What do we know about the two solution curves? Or not the two solution curves, the the dx dt and the dy dt. So check out those problems, play around with those problems. I think what I might do is I might post like solutions for a selected few of those so you can see practice on those. You've also got notes to finish up before next time, and damn it, it's already 8 o'clock. Shit, I thought we were gonna have time to take a look at, put you into groups and have you take a look at the investigation. So here's what I'll do. I'll shut up. I'll let you guys work if you want to talk with your group mates about what's going on with the investigation, because you got to work together on that. And then if you're done, you're done and you can take off. So I'm going to